Hey, welcome to Forces and Newton's Laws of Motion. Let's get on it. So, force is a concept that's super important in AP Physics 1. So, let's make sure we get our heads wrapped around it right away. So, what is a force? A force basically is any push or pull action that acts on an object. Now, what's so important about force is if no force is acting on an object, then it will not accelerate. It takes a force to cause an object to change its motion or accelerate. So the thing to keep in mind is that there's no force acting on an object. Or another thing of that is if there's multiple forces acting on an object, but they all cancel out and sum to zero, then the object is not going to accelerate. It can move, it just can't change the way it's moving. So objects can travel at a constant velocity without a force, but it takes an overall non-zero net force to cause an object to accelerate. So here I have an object that's at rest, no force acting on it, so it's not going to accelerate. I apply a force to it, I push on it, and it's going to accelerate while I'm pushing it. As soon as I stop pushing on it, it's going to stop accelerating and continue with the constant velocity that it got as a result of the force I did place on it. Now, when we go to measure this, we're going to measure these forces in units called newtons, named after Sir Isaac Newton, basically the father of modern physics. All the physics you're going to be studying in AP Physics are basically courtesy of this man. So, what is our definition of a force? Well, 1 Newton of force is defined to be the amount of force it takes to cause 1 kilogram of matter to accelerate at a rate of 1 meter per second squared. There you go. That's a Newton. So now we're going to use Newtons when we talk about forces. So let's try this here now. So forces are vector quantities. They have a directional component to them, both an amount and a direction. And so what we find then is the direction at which an object accelerates is a consequence of the force. Objects will not accelerate without a force applied. Whatever the direction of the force vector, that is also the direction of the acceleration vector. So let's try this here. I have an object at rest. I place a force in the positive direction. Well, then the object is going to accelerate in the positive direction. Now, if I continue to apply a force in the positive direction, then it's going to continue to accelerate in the positive direction. And if its velocity is also in the positive direction, then it's going to increase in speed. However, if the object has a velocity vector that's oriented in the positive direction, and I apply a force in the negative direction, then it will accelerate in the negative direction. So now I have a positive velocity vector and a negative acceleration vector. The object is going to slow down and eventually stop. So here I just have some illustrations of a large velocity in the positive direction, force acting in the negative direction causes a negative acceleration. The object will slow down, stop. If I continue to apply that force, now it will speed up in the negative direction, and it will continue to gain speed in the negative direction because now the force vector and therefore the acceleration vector are acting in the same direction as the velocity vector. Let's try it here. I have an object traveling at a high velocity in the negative direction when I apply a force in the positive direction. That causes acceleration in the positive direction. So since the acceleration vector is opposing the velocity vector, the object now slows down, eventually stops. It picks up speed in the positive direction. And then if I take the force away, it's going to continue at that same speed in the same direction. In other words, it will not accelerate anymore once the forces are removed from it. So it takes a force to make it accelerate, and by knowing the direction and magnitude of the force, I can figure out what the direction and magnitude of the acceleration acting on the object is. Now, remember, I said Newton came up with this. Well, Newton laid out basically 3 big ideas about motion in regards to forces. So let's articulate each of those. Newton's first law of motion, which you may have heard before, basically says that an object that's at rest is going to remain at rest, velocity of zero, magnitude of zero, and an object that is in motion will remain in motion, is at a constant velocity, same speed, same direction, unless acted upon by an external force. So just for a second, let's unpack that term external force because it is worth noting here. So let's say I have a bus here. There's no external force acting on it, so it's not going to accelerate. Now, this person is not inside this bus, so he is external to the bus. And when this person puts a force on the bus, that bus is going to accelerate if the net force is non-zero. So an external force acting in this positive direction is going to cause the bus to have an acceleration in the positive direction. But let's take the same thing and put the person inside. Now it's now an internal force rather than external force. Well, he's not going to accelerate because what happens is his hands may be pushing 100 newtons to the right, but his feet are pushing 100 newtons to the left, and those two forces are going to sum to zero, and it's not going to accelerate. So that's why I have that term external force. Now, Newton's first law is essentially a statement about a concept called inertia. Inertia is simply the the degree to which an object resists changing its motion, resists accelerating. So the more inertia you have, the less you want to change your motion and accelerate. So what causes the object to have inertia is simply one thing: mass. Objects have inertia because of their mass. And that brings us to Newton's second law of motion. Newton's second law of motion says that the acceleration of an object is going to be directly proportional to the amount of force applied to the object, but inversely proportional to the mass and therefore inertia of the object. So the best way to think about Newton's second law rather, is this way here. Acceleration is equal to force over mass, directly proportional to force, inversely proportional to mass. Now, the truth is, it's often written a different way just to make it easy, which is just F is equal to ma. So I just rearrange this. F equals ma is something that is one of the few physics equations that everybody's parents probably know. And that's the most common way to write it. All right, let's just take a look at the consequences and just get our head wrapped around. So here I have an object at rest is going to remain at rest unless an external force acts on it, Newton's first law. Now I apply that external force, so it is going to accelerate. This mass is going to accelerate as a result of this force. All right. Now, what if I double the amount of force? Well, if I double the amount of force, since it's directly proportional to acceleration, I'll also double the acceleration. On the other hand, if instead of doubling the force, I double the mass, so now I have twice as much mass. If this becomes a 2, since this is inversely proportional to mass, if I double the mass, I cut the acceleration in half. That's Newton's second law. It's super important and mercifully super easy to understand. The reality is slightly more complicated, however, because there's usually more than one force acting on an object. And a lot of what we're going to do in this unit is try to disambiguate all these different forces using different techniques. So a better way of writing Newton's second law, a more appropriate way, is to use the summation sign. So this capital sigma simply means the sum of. So the sum of all the forces acting on an object is equal to mass times acceleration. And we'll talk about how to determine the sum of the forces in future lessons. But for right now, I'd just like to get that out there. So uh, sometimes we say if the forces sum to zero, that they are balanced. What that basically means is for every force acting in one direction, there's an equal force acting in the opposite direction. They cancel each other out. So let's just take a look at this here. All right, now this object could either be in motion or at rest. It doesn't really matter. If I applied 10 newtons in the positive direction and 10 newtons in the negative direction, since force is a vector quantity, negative 10 plus positive 10 is going to sum to zero. And since the net force is zero, the object's acceleration is going to be zero. It's going to continue with whatever velocity it has, be that zero or some other value. On the other hand, if the forces are unbalanced, in other words, they do not sum to zero, it's a different matter. So now I have 10 newtons of force acting this way, but I have 30 newtons acting in the negative direction. So now I'm going to sum them. I'm going to say 10 plus negative 30. When I sum that, I get negative 20. So negative 20 newtons of force, sum, acting on 5 kilograms of mass is going to cause an acceleration in the direction of the force, which is the negative direction, of negative 4 meters per second squared. Now let's talk Newton's third law. I'd say this is one that most people misunderstand, but don't worry, it's not that hard and we're going to get you there. Maybe not in this screencast, but in future ones. So Newton's third law basically states that basically a force requires two objects. A force is not something that stands alone. A force is something that exists between two objects. All right, and if one force acts, if one object pushes on the other one, it's the other force pushes the other object pushes back with an equal amount of force. I'm not going to edit that out. I should, but I'm not going to. I'm too far into this. Okay, so let's just say this again. So basically, for every force exerted by one object on another, there's a force exerted of equal magnitude in the opposite direction. So I have two objects. The force acts between them. So when this person pushes on this cart pushes on the person with the exact same amount of force. So, and they're in opposite directions. And there's no avoiding that. For every force produced, there is another force produced in the opposite direction with an equal magnitude. That's Newton's third law. So you can't push on something without it pushing back on you. Now, that doesn't mean you're going to accelerate the same. So look at this. The person wearing roller skates has mass m, but the cart on roller skates has mass 2m. Now, when this person pushes on the force, that force acts not just on the cart, but on both him and the cart. It acts on both objects. It takes two objects to have a force, and the force is the same, but in opposite directions. So force F acts on this one, force F, negative F acts on this one. This person is going to accelerate backwards at negative A, but this one will accelerate forward at positive 1/2 a because it has twice as much mass. Newton's second law. Now, there are a number of forces that we need to pay attention to in this course. So I'm just going to go through them now, and we'll get used to them as we practice things. Okay, so we have the normal force. The normal force is basically the force that acts between two surfaces that are in contact with each other. It keeps one object from sinking through the other surface. I put a coffee cup on the table. It's the force that keeps the coffee cup from sinking through the table. All right, so it's the thing about you need to know, it's always perpendicular to the surface. All right, no matter which orientation of the surface, the normal force is perpendicular to that. Friction force. So friction force acts between two surfaces that are trying to move past each other, uh, and it always acts parallel to the contact between those surfaces. So the normal force acts perpendicular. The friction force acts parallel to. Tension force is basically uh, a force that acts between two objects that are connected by a string or rope or a chain. And one thing you've got to keep in mind is uh, that both ends of a string have to be pulled with the same amount of force. If I'm pulling this way on this end, I'm pulling the same force on the opposite. You can't have more end on one than the other because of Newton's third law. And then we have a catch-all term. We say applied force. Uh, so if you just push on something, that's the applied force. If a car is causing something to move, that's the applied force. If a donkey's pulling, it's an applied force. It's just a general term for I want there to be a force on the subject. I almost forgot the biggest one, the most convenient one to use of all, and that's gravitational force. So the gravitational force is acts on any matter is going to be pulled towards a planetary surface. We'll get more into details later on in this year. But the thing to keep in mind is the gravitational force always acts in the downward direction, towards the center of the planetary surface. So let's try this. I got a 5 kilogram box sitting on the floor of an elevator at rest. Oh, you're going to love elevator problems. So I want to know, what is the gravitational force acting on the box? Well, it's just going to equal mg. So you take the mass times the gravitational acceleration, g, 10, and that's the weight of the object. So if I have a 5 kilogram object, the gravitational force is going to be negative 50 newtons. 50 newtons in the negative force. M, 5 times G, negative 10, gives me negative 10 newtons of force, negative 50 rather, newtons of force in the downward direction. Well, this thing is just sitting still. So what's the normal force acting on it? Well, this object's not accelerating, so therefore the sum of the forces must be zero. If there's negative 50 newtons of gravitational force acting in the downward direction, there must be a positive 50 newtons of force acting upwards from the contact between the two surfaces. So the normal force is 50. And that's normally the case when we find things just sitting on a floor. The normal force is just going to be equal to mg. But let's change it now. All right. Aha. Now the elevator is accelerating upwards at 4 meters per second. It's accelerating. What's the normal force acting on the box now? Well, here's the thing. Gravitation only cares about the mass of the object. So the gravitational force is always going to be mg. So the force of gravity plus the force of Newton's, that's the normal force, that's the sum of the forces, and that's going to equal ma. Sum of the forces equals ma. Let's sum up our forces. Well, I have negative 50 newtons is the gravitational force. I don't know what the normal force is, but I do know this. I have a 5 kilogram mass that's accelerating in the positive direction at 4 meters per second squared. So if I solve this for the normal force, I see that the normal force is positive 70. And that makes sense. There's an unbalanced force. I have more upward force than I have downward force, and that's why it's accelerating in the upward direction. Now, uh, what if the elevator was accelerating in the downward direction? Okay, so now I have it accelerating downward. So I know there's a net downward force acting on this object. Again, I'm going to say the sum of the forces, in this case, gravitation and normal, is going to equal ma. Sum of the forces equals ma. I always know the gravitational force. It is mg. 5 kilograms times negative 10 meters per second squared for gravity gives me negative 50. I don't know what the normal force is, but I do know this. I have 5 kilograms of matter and it happens to be accelerated in the negative direction, downwards at 4 meters per second. So per second. So if I solve this, I'm going to find the normal force is now 30 newtons. Well, let's see what that means. If I sum up my forces, what do I get? Negative 50 plus positive 30 gives me negative 20, and it says negative 30. Please pretend I didn't do that. Okay, sorry about that. I'm going to fix this before you actually look at the slide presentation. I think that's all I've got for you here. Thank you for watching. I know that was a long one. See you later.